So in this lecture screencast, what we're going to do is continue our discussion of building Lewis dot structures using the periodic trends, specifically electron configurations, where we're utilizing valence electrons to help us determine the bonding. And what we are going to do is convert a condensed formula such as hydrogen, methane, ammonia, water, hydrogen fluoride into a Lewis dot structure. So we've already done this in class, but let's just go ahead and review it. So if we are given a condensed formula like this, we need to be able to convert it to a Lewis dot representation and a bond line formula. So what we'll do is look at the constituent elements of each molecular formula. So in H2, obviously there's two hydrogens, so each hydrogen atom supplies one valence electron. So we have H dot bonding with H dot. So those two come together to form the molecule, and then we can represent that as H with a single bond between them. So now with methane CH4, we have one carbon, four hydrogens. If we count the electrons total that we need, so carbon, we need 4 electrons. Hydrogen, we need 1. And then we have to multiply that by the number of each type. So this is 1. We get 4 valence electrons. We have 4 hydrogen atoms. So we should have 4 electrons there. So overall, we should be showing 8 total electrons in that molecule. We know that the carbon supplies 4 of them. And then the 4 other individual hydrogen atoms are going to supply each their own valence electron. So that's 5, 6, 7, and then 8. So there we've shown our 8 total electrons that we need to show for methane. And again, if we were to convert that into the line formula, we would just show the pairs as a line. And it's important to remember that, as humans learning this is just a way of communicating what this structure is. So the letter CH4, that means methane. This Lewis dot structure means these things. This line formula here, all these 4 things mean the same thing. And again, we're building that up from these electron configurations. So let's go ahead and look at ammonia. We'll do the same sort of counting routine. We have a nitrogen, we have hydrogens. We see that from the electron configuration of nitrogen, we have to have 5 valence electrons, 2 plus 3. Hydrogen we know supplies 1. We have 1 nitrogen, that's 5. We have 3 hydrogens, that's 3. So we need to show a total of 8. There's our nitrogen atom. Nitrogen's going to have a lone pair and then 3 electrons available for bonding, so that's 5. Then we have the 3 hydrogens each supplying 1. So that gets us our total of 8 electrons total in that molecule. And again, you can represent the same thing for ammonia, nitrogen, lone pair, hydrogen, hydrogen, hydrogen. So let's move on to water. Oxygen is supplying 6 valence electrons. There's 1 of them, so that total is 6. Hydrogen supplies 1. There's 2 of those, so that's 2. So again, we're showing 8 electrons total. Now oxygen has 2 lone pairs, 2 sites to bond, so that's 6 electrons. Each hydrogen supplies the last single one, so that gets us our 8 total electrons. Then we can draw our water. with the central oxygen bearing 2 lone pairs. Finally, fluorine is supplying 7 valence electrons. There's 1 of them, so that gets 7 electrons from fluorine. Hydrogen supplies 1 valence electron. There's 1. So that gets us 8 total electrons we have to show. Fluorine, halogens in general have 3 lone electron pairs. There's the free valency, the hydrogen bonds with the other. So that gets us HF. And on heteroatoms, we typically want to show our lone pairs. So again, what is a heteroatom? Nitrogen, oxygen, halogens. So notice the trend as we're moving across the periodic table. NOF, we have 1, 2, 3 lone pairs. And as you want to start thinking in the big picture of why this is important, if we're showing just strictly, say non-polar covalent bonds, or we have polar covalent bonds and lone pairs, the electron density around the atoms, as we can see, starts to affect things like the melting point, the boiling point, the physical state at room temperature. Another way we're going to start communicating about these molecules is in general as their functional groups. So hydrogen is its own functional group. There can be no other derivative of hydrogen. Alkanes, the ANE ending, that's a hydrocarbon. The C1 alkane is methane. Amines, the simplest amine is ammonia. Alcohols, the simplest alcohol is water. These mineral type acids, hydrogen fluoride, that's the simplest ones. So we can move down the halogens to form hydrogen chloride, hydrogen bromide, hydrogen iodide. Those are acids. So what we're going to do in this next slide is we're going to add this group to the free valencies of each of these. So the molecules that we're going to make, I've already shown here. We're basically going to take this species here, CH3, with an open valency, bond it to each of these where the other valencies have been added to hydrogen. So we're going to make methane, ethane, methanamine, methanol, fluoromethane. So you can see we're starting to get specific with how these things are named. And down here are the functional groups. So methane and ethane are both alkanes. They end in ANE. The group bonded to the amine, that's an amine, that's called methanamine. The meth comes from, it's a C1 carbon. The alcohol ends in OL, you see that here. Methane is converted to methanol. The alkyl halide, this is fluoromethane. So this is a 1 carbon alkyl halide. So again, what we're going to do is bond this to these existing atoms to make these. So let's go to the next slide here and do that on an open template here. So here's our Lewis dot representation. I'm basically going to bond each one to this. So here we're going to make methane. So H, that supplies 1 electron. We've bonded the CH3 with its electron. So again, this is methane. So methane is a non-polar molecule, and we'll review the dipole moment data on the next slide. So what we're going to do now is for carbon, I'm going to fill the rest of these 3 open valencies with hydrogen. So that's going to give us CH3 dot, and we're going to bond that with CH3 dot. So that's going to give us ethane. So what we're doing is taking H3C, bonding that with H3C. So those will come together. And so if I show that central bond, and then I'll show all the other hydrogen bonds as such. So this is called ethane. So notice the ANE is indicative of the hydrocarbon alkane functional group. The prefix of the name tells you how many carbons there are. So meth is 1, eth is 2. So in our next example, we're going to take CH3, bond it to this group here, where we've filled in these last two valencies here with hydrogen. And again, the reason we're doing that is just to see what is the basic bonding pattern of some fundamental functional groups we're going to be learning here over the next module. So notice that the central bond here between carbon and nitrogen, that's going to become a bond. The lone pair remains intact. So this would be called methanamine. So the suffix of the name gives you an indication of the functional group. The prefix of the name tells you really how many carbons are in that functional group. So this is methanamine. So the next functional group we'll look at is bonding our H3C with one of the open valencies of the oxygen, where the other one has been taken up by the hydrogen. So you can see it takes quite a while to write all these little dots down when we're keeping track of the octet. So if we convert those to lines, which signifies that they're bonds, that reduces the burden a little bit. Again, this is called methanol. This is of an alcohol functional group, so that's why the suffix ends in OL. Notice on the heteroatoms, nitrogen and oxygen, it's always good practice to show the lone pairs, because as we move into module 3 and we're showing how electrons move, you want to know that those heteroatoms have those lone pairs of electrons. Finally, our last example here, we're going to bond the H3C plus the halogen. So we're not putting any hydrogens on the halogen because there's only one open valency, so we're just bonding those two together. And now there's 3 lone pairs on the halogen, and we can convert that to fluoromethane. So this tells you that if you look at this starting compound here, we made methane. What we did was substitute out a hydrogen for a halogen, and so we can call this fluoromethane. So again, part of our initial learning of organic chemistry is how we communicate structure. So what we've seen over the past couple of slides is how to build structures, and now how we communicate them through names, that's nomenclature. This type of bond line structure, Lewis dot structures. And so contingent upon all of this is that you understand, these bonding patterns that you have to work with starting from atomic electron configurations. So as we can see in this slide, the structures are drawn out for you. Let's just take a moment to look at this last item here, determine dipole moment, and that's based off electronegativity. So these are Pauling electronegativity values. So carbon's 2.55, hydrogen's 2.2, that's a difference of 0.35, that's less than 0.5. So let's write that down. So we'll say 0 is less than delta electronegativity is less than 0.5. That's non-polar covalent. Then we can say 0.5 is less than delta En. That's the change in electronegativity. So the difference between the two elements is less than about, we'll say 1.8 to 2.0. This would be a polar covalent. And then we're talking about the bond type here. So methane and ethane, these are both non-polar covalent bonds. So if you look, all these CH bonds are the same. The CC bonds here, you can see that because the two values are the same, it's 0. So this is a non-polar covalent bond. And all the rest of these CH bonds are the same. So this overall, because the bonds are all non-polar covalent, the molecule is non-polar. When we get into this situation here where there's a heteroatom nitrogen, we can now see that the difference between the nitrogen and the carbon, that puts us in this region here, so we have a polar covalent bond. Additionally, same looking at the nitrogen-hydrogen, that's a polar covalent bond. So now we're getting into a polar molecule because we have this functional group with a nitrogen lone pair that's concentrating electronegativity around this atom here. You can see the same for this oxygen. So again, we're in this region where you have these two scenarios, CO, HO, those are polar covalent bonds. So overall, this is going to be a polar molecule as well. And then fluorine, as we're moving across the periodic table, fluorine's the most electronegative element. So CF is polarized. So this is a polar molecule as well. And you can see in our heteroatoms here, nitrogen has one lone pair, oxygen 2, halogens 1, 2, 3. So just to review on this last slide here, molecular weight. Again, how do we calculate that and what is it used for? So if we look at methane, for example, methane has atomic mass units of 12. There's 1, so that contributes 12 to the mass of the molecule. So I'll just write up here AMU, then here I'll write number. So hydrogen's 1, there's 4, that equals 4, so we add that together. That's how we get this 16 right here. So what about ethane? Let's do the same thing. CH, carbon's 12 times 2, that's 24. Hydrogen's 1 times 6, that's 6. That gets us our 30. So we can do the same sort of analysis for methanamine, methanol, fluoromethane. Now, if you look at these molecular weights, especially ethane, methanamine, methanol, fluoromethane, they're really not changing a whole lot. So when we describe, how does structure and functional groups affect physical properties such as melting point, boiling point, physical state, using the molecular weight of the molecule is really not a good explanation. You have to look at the other intrinsic things in the molecule as we just did, such as the dipole moment. So you can see that these molecules here are starting to have dipole moment. So we have these dipole-dipole attractions. We can have hydrogen bonding scenarios. So that's why you see these large jumps, for example, in melting and boiling points. And again, the last row here tells us the type of functional group these specific molecules reside in. And again, as we move on into the semester, we're going to learn the general reactivity of different functional groups. And once we know reactions, then we can start doing sequences of reactions, and that's how we can make more complex molecules. So in this slide, what we're going to do is start looking at the alkane functional group. So alkanes are hydrocarbons. And hydrocarbons are exactly that. They're molecules that strictly have hydrogen and carbon. There are a couple different types of hydrocarbons, and this is the first one we're going to look at is called alkanes. So in this slide, you see this column here called C count. That's the number of carbons in the alkane. This is the name of the alkane. This is the molecular formula. The molecular weight's going to go here. We're going to calculate that first. And then this is just physical data that I'm giving you that is known. So I don't expect you to ever memorize data. What I do expect is that you'll be able to explain it based on things like dipole moment, electronegativity, those type of factors. So we've seen already methane and ethane. So when you see this, you should think this molecular formula. So we just calculated what that was. It was 16, right? And we did the same for ethane. That was 30. So what I want to show you now, moving past ethane to propane, the difference between propane and ethane, if you allow me to say C3H8, that's propane. Now the difference between that and ethane minus C2H6, this is C1H2. So we know that one carbon is 12, two hydrogens is 2, so that's 14. So the difference between here to here is 14 additional mass units. So propane should be 44. And you can do that because if you take 3 times 12, that's 36. Then you add 8, that's 44. So if we do the same thing for going to butane, C4H10. So you can see the difference between these two is C1H2. It's always going to be that in this series that we're looking at now. So the molecular weight of that's going to be 58. Now what is new to us? Moving down this carbon count, see we have one of each, one methane, we have one ethane, we have one propane. We have one for those carbon counts, right? 1, 2, 3. There's only one name listed. But when we get to the C4 carbon count, now there's 2. Butane and then 2-methylpropane. See how they both have this same molecular formula? So in a sense, the molecular formula can be ambiguous because it has the same molecular weight. So of a carbon count of 4 total carbons with a molecular formula of C4H10, we can actually have 2 different compounds. So I want to investigate that on the next slide. So to build up to that carbon 4 count, we've already seen methane, we've seen ethane, propane, so we have methane, ethane, propane. So given these molecular formulas for the first 3 here, there's no other way that you can take these elements and build a molecule other than what we've drawn. But as we see with the carbon 4 count, We have butane and 2-methylpropane. They both have the same molecular formula. They both have a mass of 58. So what I want to do is now show you a way of drawing isomers. These compounds are called isomers because they have the same molecular formula, but they have different connectivity. Now the way we're going to do this, to be very logical, we're going to start with this 4. I'm going to write the number 4 there. Now I'm going to write all the carbon atoms out in a chain. 1, 2, 3, 4. So I've written those 4 carbon atoms out. Now I need to write 10 hydrogen atoms. So the terminus has to have 3 because it has 3 open slots. This internal has 2. This internal has 2, and this last terminus has 3. So that's 3 plus 2 is 5, plus 2 is 7, plus 3 is 10. So that gets us our C4H10. That's butane. So this is called a linear alkane. This next compound here, 2-methylpropane, is a constitutional isomer of butane, and this is a branched alkane. And why do I say branched? Because when we wrote out this C4 isomer, we've maximized, there's no other ways we can write these carbon atoms in a linear fashion. So what we're going to do now is move down to a 3-carbon linear chain. C, C, C. So we're looking to draw 2-methylpropane, which is a constitutional isomer of this. We've drawn 3 carbons. We need to add 1 more. So where do we add that last carbon? We can't we can't connect it at the terminus because that just gets us to the C4 chain. So we have to put it in an internal carbon. So that gets us our 4 carbons. Now if we look, we have 3 open valencies, 3, 3, and 1. So that gets us our 10 hydrogens. So rather than drawing the bonds, I'm just going to draw in these groups here. And it's incumbent upon you to understand that the way this is represented, this CH3, can be condensed into that. This really means this. CH3, this is another way of showing that. Now the exercise we were doing in class before with this C13-1H and then ratio, this is really to help us think about spectroscopy, again, which is imaging of the molecule. And what we're going to do is look at the molecule, write down the unique number of carbons that we see, and you're going to see that this exercise helps us differentiate constitutional isomers. So what I'm going to do in red, first the laser pointer, I'm looking at this molecule. I see CH3, CH2, CH2, CH3. The terminal CH3 groups are the same. The internal CH2 groups are the same. So therefore, I can say that this molecule has 2 unique carbons. It also has CH3, CH3. That's one set of proton, CH2, CH2. These are identical, so that's 2 sets. The ratio of those hydrogens is 6 to 4. Now, why this is important is because the sum of that is 10, right? 6 plus 4 is 10. That's the total number of hydrogens in the molecule. And what these first 2 numbers are telling you, in the carbon NMR, you're going to see 2 peaks. The proton NMR, you're going to see 2 peaks And those peaks are going to be in a ratio of 6 to 4. And in NMR, we call that ratio an integration. It's the area under the curve. So how does this same type of analysis work for this constitutional isomer called 2-methylpropane? We have CH3, 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 CH. So we have 3 CH3 groups and 1 CH. So that gives us 2 unique carbons. Now for the hydrogens, it's going to track the same. The CH3 groups are all the same. The CH is different, that's 2. Then the ratio of them is 9 to 1. So see how these differ now? Even though you have 2 and 2, 2 and 2, these ratios for those 2 peaks are now different. So we can use that form of imaging to tell us which one of these constitutional isomers we have. So let's go ahead and go through the pentane constitutional isomers, and I'll let you work out on your own the C6, the hexane constitutional isomers. So pentane is a linear alkane. So I'm going to start here 5. It's linear. C, 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 C. We can even help ourselves by numbering here 1, 2, 3, 4, 5. We need 12 hydrogens. C1 and C5 both get 3. So that's 6. C2 and C4 both get 2. C3 gets 2. So what is the classification of these? How many unique types of carbons do we have? So we can do this in a sort of another way of keeping track. We can say 1 equals 5, 2 equals 4, and then 3 equals 3. So basically, this is telling us there's 3 unique type of carbon. Same thing for the hydrogens. The CH3 groups at 1 and 5 are the same. The CH2 groups at 2 and 4 are the same, and the CH3 group, or the CH2 group at 3 is itself identical. So that's going to give us 3 as well. And the ratio is going to be 6 to 4 to 2. And again, the sum of that is 12, which we see in the molecular formula. Now you might have a question, 2, 3, and 4, carbons 2, 3, and 4. They're all CH2 groups. But 2 and 4 are the same type, while 3 is different. And the test of that is, if you're walking along the chain from 1 to 2 to 3 to 4 to 5, or 5 to 4 to 3 to 2 to 1, it's how you see those different CH2 groups. If you're standing on 3 and you look out to 4 and 2, they look the same to you. But if you're looking down at yourself on 3, it is not the same as 2 and 4. So we've exhausted the number of carbons we can put in a line. So we're going to go to 5 to 4. 4 now, again, is a butane chain. So that's why this name becomes 2-methylbutane. So I'm going to write 4 because I'm just keeping track. Of the longest chain. Now 5 minus 4 is 1. We have 1 carbon to deal with. And really we can only put that 1 carbon at 2 or 3. If we put it at 1 or 4, we're just making a 5 carbon chain. So let's go ahead and put that carbon in. That's the last carbon atom. I'm just going to say C5 just because we're keeping track of the number of carbons. Go ahead and put in our open valencies for hydrogen. This has 3. This has 3. We're showing 1, 2, 3. This has 1. 1, 2. This has 2, CH2. This has 1 open, 1 bond. So it has 3 hydrogens. So that may look a little bit messy. So I want to show that in another way, where the hydrogen atoms themselves are all now implicit. So I'm going to represent a carbon-carbon bond like this. And really, what I've drawn right now could be considered ethane. So if I consider this carbon 1, this carbon 2, I draw in that CH3 group bonded to it. So we can see here's our longest chain, 1, 2, 3, 4, 1, 2, 3, 4. And all I've done is really, I've made the hydrogen atoms implicit. You see the 1 bond here, that means there's 3 hydrogen atoms. You see 1, 2, 3 bonds, there's 1 hydrogen atom. 1, 2 bonds, there's 2 hydrogen atoms. 1 bond, there's 3 hydrogen atoms. So now if we do the same sort of analysis as we did up here, and I want to put this number 5 back in, we can see that 1, 5, and 4 are all CH3 groups. But only 1 and 5 are equivalent because they're both bonded to 2. 4 is not equivalent to 1 and 5. So 1 equals 5. 2 is a CH group. There's no other CH groups in there, so 2 equals 2. 3 is a CH2 group. There's no other CH2 group, so 3 equals 3. 4 equals 4. So when we count that, we have 1, 2, 3, 4. That tells us there's 4 unique carbons. We do the same for the protons. And again, the protons at 1 and 5 are the same because they're both in the same sort of bonding environment to 2. However, the CH3 at 4 here, it's not the same as those. So we have 1, 2, 3, 4. We have 4 unique type of proton. Now the ratio, I'm just going to say, is 6 to 3 to 2 to 1. Where did we get that? 3 plus 3, that's our 6, 3, 2 hydrogens, 1 hydrogen. So let's keep these numbers straight. The numbers that I'm putting here, that's strictly helping us determine the longest chain so we can draw these isomers. These numbers here are the ratio of those hydrogens bonded to those carbons. So as you can see, for pentane, with a constitutional isomer that's linear and one that's branched, now these numbers differ, right? So if you were given a proton NMR and one had 3 carbon, or one had 3 peaks and the other had 4, you could immediately tell it would be this stereo or this constitutional isomer based on the number of unique sets of proton signals. So I encourage you the same sort of exercise for hexane isomers. Now you see there's 1, 2, 3, 4, 5. There's 5 isomers you should draw, and you should determine these values for each of them. So what you're going to see here, and the numbers I'll write in red. So hexane is linear. Now we're getting to pentane. There's 2 of those. So the longest chain in there is 5. Then we get into butanes. The longest chain in there is 4. What you're going to find if you go through this same analysis, that all of these will have all different carbon and proton numbers. So you can identify what the constitutional isomer is based on the data that you're given. So this last entry here, N, what does that mean? So as we said, this functional group alkane, which we see here, for an alkane, the general molecular formula for an alkane is CnH2n plus 2. So what does that mean? So for example, let's look at that hexane where N equals 6. We have C6, H2 times 6 plus 2. That's 12 plus 2. So that gets us C6H14. So that's where you see these numbers come from. So the general molecular formula for an alkane is CnH2n plus 2. And so if you've gone through this exercise of writing these hexanes constitutional isomers, these are the different carbon-13 proton ratio values that you should get. So go ahead and look at these values, see how they match to yours, and if you're able to think about how to analyze these structures according to that concept. So in this screencast, we've looked at building some Lewis dot structures, looked at things like electronegativity and how that affects physical properties. We've then looked at the alkane series of functional groups, what happens as we're moving up the carbon count for a particular molecular formula can give more than one compound. Those compounds differ by connectivity of CC or CH bonds, so they're called constitutional isomers. And this concept here of carbon-13 proton and ratio helps us differentiate those constitutional isomers.